So last time, as we were looking at a lot of these things, somebody pointed out, hey, isn't this just chapter 22, but like more? And I was kind of forced to concede, yeah, it's really a lot of the same thing, right? Chapter 22 started by talking about forces, and then at the very end we started talking about, let's look at something called the electric field, which emanates from all charges and is essentially how forces know to exert force, right? It's how they know that they're there. It's how a charge actually exerts a force on another thing. It does so through the field. But we started from the field from a single point, and then we made the point, what if we have multiple charges? What if we have multiple charges at different points? What does the electric field look like then? And we realized, hey, would you look at that? They just add up together. And that was super nice and super useful. And do not discredit that. That is a very nice thing. But we only did a handful of charges at best, right? We got up to 4 charges, and that was kind of nasty already, if I'm being completely honest, right? There was a lot of work that was going into that and everything else. So if we look at any sort of real object and how many electrons are needed to make any sort of charge like what we've been looking at so far, we've got more than a handful of charges. It's quite a few more than a handful of charges. How do we deal with nearly an infinitesimal number of charges, right? At least from our perspective, that's so many different charges. How can we actually possibly deal with all those? Well, that's what today's about, right? Charged objects. So no longer point charges or anything else like that. What if you have a charged object and an object gets charged by having many electrons, or a lack of electrons and many extra protons with no electron partners? So you can imagine first, if we look at an object like what's on the left here, right? This circle, or a sphere rather, that has some amount of charge on it. And let's assume it's a charge all the way throughout this entire thing, right? It's just like every piece has the same amount of charge on it. Well, it's not really different from a point, right? We can still kind of agree that that's a point. It looks like a point. What we're going to find later is it behaves like a point. That's just a big point charge, more or less. As long as we're outside of that thing, it turns out it doesn't matter. But what about the object on the right? That's like I took my point and I dropped it down the stairs or something. Right? That is no longer such a clean, consistent thing like what's on the left. Now, if I wanted to find the net electric field from that object, we could imagine that what we would have to do is look at every single individual charge inside of that object and find the electric field because of that single charge, and then sum up every single charge altogether. Right? And so if that tiny piece of charge was called dq, then the tiny field that it created would be dE, and then we would have to sum up all of those things to find our total electric field E, right? Kind of what's shown in the equations here. A really tiny charge dq makes a really tiny field dE. If I want to find the total E, I've got to sum up all of those things. And how do you sum up when you have many things, right? An uncountable number of things. Calculus gets involved. Now, here's a problem, though. If I'm going through this, and I've set up my integral, how do I integrate over every q? What does that mean? That would mean that we would have to look at every single charge, find the magnitude of that charge, the sign of that charge, the distance away from our point that we're interested in, and the direction of the field at that point. Take all of those and sum them up for as many points as we have. And maybe you can already kind of see this is not a feasible endeavor, right? This is going to be something. Because if we really get into it, if we actually look at this object in any sort of detail, let's imagine that I've got my first piece up here in the top, dq1. Well, it has its own r1, it has its own r1 hat, and it has its own contribution to the field. dq2 is going to look different. dq3 is going to look different. Every single one of those pieces is going to be different, and there's no consistent way to describe them to actually do something practical. So objects like that, what we're going to find, it would sure be nice if we could find the electric field, but an object like that might be a little bit out of our wheelhouse. But what we do need to do is we need to figure out some way that we can define every single piece in some sort of cohesive method so that when we actually do calculus on this thing, we're not actually summing up every piece, we're doing calculus and using the tools of calculus to do most of the work for us. Right? Just in the same way that you could do an infinite number of Riemann sums to empirically calculate the area under a curve, but why would you unless you really had to? Right? If a computer does it for you, that's one thing, but if you've got to do this by hand, you're going to prefer to take the function and actually integrate the function because that's going to be a much easier process. We're going to try and figure out how we can do the same thing here. So the first thing that we're going to need, if we're talking about how do we define every single piece of charge, we need to understand how we can describe elements of charge. There are three different types of objects that we might end up talking about here. One-dimensional, two-dimensional, and three-dimensional. And at first you might be like, well, why would we ever focus on one-dimensional objects or two-dimensional objects? Because those don't exist in the real world. And for one, you're kind of wrong because at least two-dimensional objects do exist. Graphene being one example, and there are some other two-dimensional materials coming out. The thickness on per atom basis, they actually behave a lot more like two-dimensional objects than they behave like a three-dimensional object with some width to it. So two-dimensional objects do exist. However, what we're going to find is that there are plenty of different circumstances where a one-dimensional or a two-dimensional approximation of an object actually gets us really oftentimes all the way there. It's a much simpler way to talk about an object, and if it gives us the exact same answer, we're going to go with the simpler way. But anyways, for every single one of these, let's imagine I have some sort of object and it has a total charge capital Q. So if I start with a rod or a wire of charge, it's got a length L to it. If I was to look at a single piece of this charge, I would need to know about the charge density on the whole object. And the charge density is defined as the total charge divided by, for the rod, the length, right? And that's a linear charge, so that's coulombs per meter. Using that, we could say, okay, well, the charge density is this, and just in the same way that we might calculate the mass of something using a mass density or anything like that, we can say, okay, how much charge do I have on this tiny little piece? And to do that, I would have to say, okay, well, it's going to be lambda times whatever the length of that tiny piece is. And if we're doing calculus, right, we like infinitesimally small pieces. That means we're not taking some delta x, we are taking a dx, an infinitesimally thin piece of this rod, gives us an infinitesimally small piece of charge, but it does so in a way that's consistent that when we integrate over the entire thing, we get back our total charge. We can do the exact same thing with a two-dimensional object, right? Where it's got some sort of surface area, and we can say, okay, we'll take the entire charge Q, divide it by that surface area A, and we get the surface charge density, right? Coulombs per square meter. Now again, if we want to talk about our tiny piece of charge, now we've got essentially two dimensions. It is a unit of area. What's the tiniest piece of area that I can take? dA. When we actually apply this in a problem, that might be, dA might be equal to dx dA, and that's essentially a tiny little width and a tiny little length, and that's what tells us about our piece of charge, right? But broadly speaking, no matter how we define it, it's going to be some tiny unit of surface area, dA. And again, if we integrate over the entire thing, that we get back our total charge Q. And finally, volume density is another one that we can do here, naturally, right? What we usually think of when we're thinking density is for volume, but that's going to be the charge divided by the total volume of the object, if this cactus had charge, for example, right? I would take a tiny cube, so maybe it's a dx, dy, dz, or maybe it's a tiny little sphere or something like that. It's calculus. I've got some options, right? But I'm taking my smallest possible volume, multiply that by the density, gives me my smallest possible charge, dq. So that's how we can define these things, right? And that's going to be pretty important because if we're going back and looking at this thing, how do I integrate over every single Q? I really don't know how. I've got to be honest. I consider myself at least an expert in this material, and I don't know how to do that, not efficiently. But I do know how to integrate dx, dy, and dz, right? Those are things that I remember from my calculus course. So I'm going to show you an example problem of this thing. This is example 23-3 in the book, but I'm going to run through this thing, and I'm not actually going to follow the slides very closely on this one. I'm going to start with the slides, but I'm going to go off and do my own thing on this of how I would actually solve this myself, right? You might notice in the slides, this is a very well written out way of how to do these things. All the steps are written out, but it's kind of more like an example rather than how somebody would actually solve it. So I'm going to do this one on paper, but for now, let's talk about this thing. So we have a rod, and it has a charge Q and a length L, okay, just like our linear charges, right? And it's a rod, and we don't say anything about the thickness, we only say something about the length, and we're some distance away from it, so I'm going to assume here this is a one-dimensional object. And that's fine, right? Treating something as a one-dimensional object is totally fine. If you have a wire or a charged rod, those will behave like one-dimensional charges. And that works. And the math all works out, and you get the exact same result. If you measured it in the lab, you would find the same result. And we'll see that soon. Next chapter, we can actually prove that. But for now, we say, okay, I have a rod of charge. And if I have a rod of charge, then the linear charge density, lambda, is equal to Q over L. Let's say I wanted to look at a single piece of charge, dq. I wanted to pick out one particular piece and look at that. Then dq would be equal to the charge density times however long that particular piece was. And in this case, we're not working with dx anymore, right? Because it doesn't have any width to it. There's no x dimension to this object. It's one-dimensional in the y direction. So instead of dx, we're going to use dy. So that tells us this is what our piece of the charge looks like, lambda dy. And we can also take a look at the field while we're here. And I'm going to go over all this a second time around when I'm drawing this thing out myself. But we can also look at this thing and we can say, okay, what's the r? How far away is this piece from my point? Well, if I draw this thing out, x is a constant value here, right? It is always this same length away, at least in the x-coordinate, but the y-coordinate might be changing as we go through different points on this rod. However, at this particular point, if I say this is something y up on the y-axis, then I can find the hypotenuse of this triangle that I've made, where one side length is L, one side length is y. My hypotenuse r will always tell me my distance, and more usefully than that, what if I change which piece I'm looking at? What if I go down or up a little bit? That equation for r still works. And this is exactly what I'm talking about when I'm talking about a cohesive way that we can describe every single point using the same equation. That's what we need. So, to actually do this integral, integration is extreme addition. So what we need to be able to do is we need to be able to describe every single point in exactly the same way. We need one consistent equation that describes every single piece, and then we need to do an integral on the rest of it to make this all work. So, now I'm going to break away from the slides, and I'm going to start to do this problem as if I was doing it on my own. First things first, I need a picture. And it's not going to be a very good picture because it never is, but it's going to be all right. Here's my point that I'm interested in, call it point P, to distance x away from this rod that we've drawn. Something like this. That seems to mix pretty well. So, and let's go ahead, I'll fill this in, why not? To that, oh, I'm still in square, huh? Let's go ahead and fill this in as if it's actually a solid rod. We'll make this look nice and clean. Oh, that looks worse and worse every day. That's okay. That's okay, right? There's our charged rod. So up here, this is plus L over 2. Down here, this is minus L over 2. And the thing has a total charge of Q. Okay. So let's hit some of these points again, right? We're talking about if we want to find the individual piece of charge. Let's imagine we're looking at this particular piece, this tiny square dq. Color this orange so that we can actually see it contrast a little bit more. Something like that, hopefully. So here's my dq. To find dq of a linear object, I need to know about essentially the linear charge density, and then how long is this piece? And we said, okay, well, the length of the piece is infinitesimally small, dy, times lambda dq, and then we said lambda is equal to q over L. So far, so good. Now, here's something. Let's see if I can move this slightly more up. Just a little bit. I need just a little bit of room to be able to draw some things here. So, I want to talk about this piece of charge, and I'm going to draw a line out here, and actually I'm going to draw it out a little bit farther than that. So like that. So this distance from the charge to the point is r. This out here is the r hat because of that particular point. This makes an angle theta with the x-axis. Now here's a tricky point, and this is also a side y. Here's a tricky point. If I move dq up or down, if I look at a separate piece, my angle's going to be changing. And in fact, one other detail that I'm going to run into here is that we can see for any positive y, I'm going to end up with a negative y component when I'm talking about my electric field. Right? In this case, theta is going clockwise when y is positive. It's always going to be negative. So I'm going to make a decision real quick. Knowing that theta is always going to be negative, let me save myself some trouble down the line, and let me just assume that theta is negative, and let me take that negative sign, plug it into r hat, and just roll with it as is. If we do that, our r hat for this point is equal to cosine of theta times I hat, because the negative doesn't affect the cosine, but it does hit the sine. And this is just an important thing for me because now I can plug in any sort of theta that I might find. I can plug in, I don't know, 45 degrees or something like that. And this would give me my positive x and my negative y components that I'm expecting to see. And you might remember that last time I was talking about when you start to feel very comfortable with r hat and what r hat is trying to describe, you'd no longer have to subscribe to the cosine theta I hat plus sine theta j hat, always from the x-axis, and deal with that. You can mix this up a little bit. R hat's goal is to tell you about how these things split into x and y. And what we're going to see very soon here is that being able to split like this is going to be very useful for us. But anyways, I've been kind of rambling on a long time without really addressing, I want to find the electric field. Come on, let's find the electric field already. So here's the process that I take to do this. I say, I would like to know what E is. To find E, I need to sum up every single piece of E. I don't know how to integrate every single piece of E. The bounds of that integration don't make any sense to me. So what I'll do then is I will replace it with something else. I'll say d of E is equal to k dq over r squared times r hat. Plug it in. What do we get? Well, now a longer integral. Now this is going to be k dq over r squared times r hat. Okay, well, I still don't understand what the bounds of integration for dq would be, but I do have a replacement for dq as well, so let's try that. I can say dq is equal to lambda times dy. Plug that in. Now what do we get? K lambda dy over r squared r hat. Ha. I do know how to integrate dy, because if I look at my picture again, I can say, okay, well, the bounds of dy, I'm going from negative L over 2 all the way up to positive L over 2. This is something that I can do. I can set some bounds on this thing, and I could do this integral. So that's a good sign, right? We're ready to actually do this integral, except I run into an issue. what is constant, what is changing inside of my integral? K is a constant. That's not going anywhere. Lambda, also a constant. Not going anywhere. We talked before, though, that R, if I were to take a different dq, the length of R would change. I need to find some way that I can describe that change in terms of my integrating variable y. So the easiest way to do that is I'm going to recognize that this is a triangle, and I'm going to draw out this triangle because we're going to use it for a few steps here. Here's my triangle, y, r, and x. And let's pretend all together that this is supposed to be a right triangle. Here's an angle theta. So at any point, I could say, okay, well, I don't know how r necessarily changes. I kind of do, but not really. But I can rewrite r as the hypotenuse of these two pieces. And if I do that, my change is now in terms of y and a constant x, and x is a constant value, so I don't have to worry about that, right? I have successfully replaced this with the variables in terms of y and other constants that don't matter in the integration. So we're set. We have a replacement for r. Let's go ahead and plug it in while we're here, right? Why not? Plug it in. What do we find? I'm going to pull out some constants while I see them. K and lambda, they're constants. They don't need to be inside the integral. Square root squared cancels out that square root. Now we're in a really good spot, except r hat also changes. What if I take a more shallow height or something like that? My angle's going to get smaller. R hat's going to change direction. Well, I do remember that I already redefined r hat as cosine theta I hat minus sine of theta j hat. So I do have a replacement for r hat technically. But we already kind of see theta does change. If the length y in this triangle changes, theta is going to change. Okay, well, we can't use theta then. We need to find some sort of substitution for theta. And what's the best way we might do that? Well, this might come out of left field for a little while, but I think you probably have all seen it at some point a long time ago. Does everybody... Well, I will ask for whoever remembers SOHCAHTOA. SOHCAHTOA is a classic, right? And I've brought this up before. I had a story where a high school math teacher of mine said, don't memorize SOHCAHTOA because you won't be able to use it forever, and I have no idea what she was on about. I still use it to this day. It's still useful, right? It means sine, opposite hypotenuse. Cosine, adjacent hypotenuse. Tangent, opposite adjacent. We've been using this to define how we break up our components for a very, very, very long time, but we might not actually remember what the definition of these things started as. The definition that we actually started as was sine of theta is equal to opposite, and when we're talking about opposite here, I mean opposite on this side, hypotenuse here, and adjacent on this side. Right? Adjacent to the angle, opposite the angle, hypotenuse of the triangle. So sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. And tangent, should we need it, is equal to opposite over adjacent. Why is that useful? Well, we have those side lengths. That means sine is y over r. Cosine is x over r. And tangent, should we ever need it, is y over x. We're almost there. We can plug this into r hat and we get most of the way there, but we have one last thing that we need to do, and that's to remember that r is not a variable we can use because we don't have a definitive way of describing that. We have to replace r, right? R needs to be in terms of y. So we take this one more step and we say, okay, well, r is square root of x squared plus y squared. That's under y. X, same deal. Replace r with what we had just found. X, not y. Now, we rewrite r hat. We say r hat is actually this thing right here times I hat minus, and this is exactly why I wanted to bring that minus in here now. Because if you don't have the minus, you have to be very careful with how you talk about y. There needs to be a minus sign in here somewhere. That's really the root of this. There needs to be a minus sign in here somewhere to take into account that from a positive y, we get a negative y component for the electric field. So we've redefined r hat in terms of y and other constants that we know how to deal with. We can finally plug this in. So all of my steps in gray are essentially the substitution that I'm plugging into my integral in this particular step. Oh, so now we plug that in. And what do we find? Oh, it's getting nastier. Okay, but I see x squared plus y squared on bottom, right? That'll actually mesh together. I can use that. But what I'm going to end up with on top here is xi hat minus yj hat over x squared plus y squared to the 3/2 power dy. Now, we have an integral that we can do. And I promise we can all do this one. What I'm going to do first, though, is I've got this kind of nasty thing. I've got a polynomial on top, and I really don't want to deal with that, especially because there's an I hat on one side and a J hat on the other. So what I'm going to do is I'm going to split this up into two separate integrals. So this is going to become, I'm going to take the x component all by itself. And this might seem like a little bit of an extra step to separate out things more, but I promise it's worth it. So we've got that piece, and then minus k lambda times the other piece. Right, this is going to become y times j hat times dy over this thing right here. Okay, now, I could integrate both of these pieces. However, I don't want to do more work than I need to, right? It's a good motto to have when you're doing physics. Let me go back to my slide real quick. Let me take a look at this thing. Let me say, okay, if I took all of these pieces together, if I took every single piece, what would happen if I folded this thing over the x-axis? It's symmetrical, right? What that means is that for every single piece in the positive y, there's an equivalent negative y piece that's going to be creating a field of equal magnitude, and the x direction is going to be the same, but the y direction has been flipped. That means that the top half of the rod, the y component of the electric field from the top half of the rod, is going to cancel out with the bottom half of the rod. what we get is this thing cancels by symmetry. And let me tell you, this is your new best friend. Canceling by symmetry, seeing the symmetry of a problem and being able to reduce the amount of work you have to do to solve that problem. Oh, wonderful, right? I'm going to try and teach you where you might be able to spot that. Got one more problem today, but with enough experience as well, you'll start to see where those things will cancel out to zero. Now, you can actually do this integral, and I do recommend doing this integral for practice, right? It is a good integral to prove that this does cancel by symmetry, but I promise you, when you finish out the integral, it does cancel out by symmetry, right? It'll sum to zero at the very end. That term goes to zero. So what that means, though, for us right now is that we only have to focus on the x direction. That's the only part that matters. So let's do that. E is equal to k lambda integral negative L over 2 plus L over 2 to the, what have I said here? X I hat dy over square, oh, not square root, x squared plus y squared to the 3/2 power. Right? All of that thing. Now, I'm sure we all have memorized the solution to this integral, right? I'm joking, of course we haven't. I haven't. And if I haven't, you guys certainly have not. There's a better way to do this. I'm going to behave like an engineer for just a little while and pull up an integral table, right? And here I am poking fun at engineers a little bit, but it's out of love, I promise. What I can do here is, you might have noticed, you might have looked at this from the very beginning, but maybe not, but in the book, Appendix A is a tiny little integral table for us to use. I have a scanned version of this uploaded to Canvas under the files. I've recently renamed the folder to Equations and Helpful Sheets. But if we go here to the top right column, we see an integral quite a lot that looks like ours. Now, here's a lesson in having to use integral tables, though. You have to be very, very careful. If you remember when we were taking a calculus course that every single integral was in terms of x and every constant was a or c or something, and maybe occasionally they'd throw a curveball and say integrate over y instead, but it was the exact same thing every single time, right? We have gone with a consistency in this integral table rather than, well, having a bunch of different variables, right? So every single time in all of these integral tables, what you are most likely to find every single time is that the integrating variable is x. X is the thing that is changing, and a is our constant value. And maybe we'll see a and b and c if we need that many constants. But most often, x is our changing variable, a is our constant variable, we work with it from there. However, in our problem right now, x is a constant value. X, the distance away, x is always the same. X is our constant, y is our changing variable. So what I'll have to do here, let me pull this over to the other side so I can copy it down correctly, because I will absolutely mess this up otherwise, is I see on my integral table the integral table tells me that the integral of, on bottom, x squared plus or minus a squared to the 3/2 power, all under d of x, is equal a squared square root x squared plus or minus a squared, yada, 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 plus or minus x. That's our final answer for that one. Okay, fantastic. We need to look at this and we need to say, okay, x is the changing variable. How does that translate to our problem? Here, it was dx. For us, it's dy. Here, their constant is a. For us, it's x. That's the translation we need to use for this. And that means what we end up finding here when we actually take advantage of that, k lambda still on the outside, that's still good. K times lambda. X is a constant variable, so I can pull it out from the integral. And that's why I don't need to worry about it. There's no a on top of this integral, because if there is a constant, we just pull it to the outside. What I'm left with is x squared square root of x squared plus y squared under plus y, right? Positive y. So I'm going to erase that because it's redundant, right? It's just positive y because we had the positive. And we're evaluating that from negative L over 2 to positive L over 2. So now that we're here, what we're going to see, okay, k lambda x over x squared. One of the x's can cancel out, right? That's fine. So I'm going to have k lambda, and then I need to plug in with what's going on over here. So I've got k lambda over x times, I plug in L over 2 first. L over 2 over square root of x squared plus L squared over 4, y squared, minus negative L over 2 over square root of x squared plus L squared over 4. Nice. Minus a minus turns into a plus. L over 2 plus L over 2 becomes L. This becomes, let me do bottom first, x times x squared, square root of x squared, plus L over 4. All of that is under, whoops, I hat, k lambda L I hat. And this might look like a final answer, and you would be almost correct. But the last thing that we need to do is put this back into terms of things that we were given from the very start, and we were not actually given lambda. We've been using lambda the whole time, but lambda is actually Q over L. So my very last step is to replace it with Q over L. It cancels out the L. What I end up with there is our final answer for this problem. You'll need to be able to do this one on your own. Realistically though, right? Let's think about this. Back in 191, the first time we saw vector things going on and dot products and cross products and a lot of those crazy things and derivatives, and those were terrifying and awful at the time, but we got through them. Right? We dug in, we chewed on them for a while, we had some questions, and that was okay, right? But eventually we got them. And even if you don't feel confident in those things going back now, if you go back to those things now, I'm sure you'll have a much better time with them, right? Just in the exact same way. This stuff looks very spooky right now, but with some practice, you'll start to get the feel for how to tear apart these problems. I really love these problems because I think they do a fantastic job of what the calculus courses kind of gloss over. The picking apart what's actually inside of an integral when you have constants and things that are changing and how you have to do those substitutions. And I feel like that's one of the big disservices of calculus courses, that they don't really cover those things in enough detail. But here we really get to explore what goes into an integral and how you actually treat integrals properly. So our first question here is why j hat cancels but I hat adds up together. This is, I think, best actually described by the picture right now. So let me zoom in on, let me not zoom in on that thing. That looks a little bit less nice than I wanted it to. So my argument here is that if we look at every single piece, if I'm taking every single dq on the positive half of this rod, right, so only from y is equal to 0 and up. If I look at every single dq, every single little orange square that I could possibly make, there's an equivalent orange square on the bottom half. And that equivalent orange square on the bottom half is going to have the exact same magnitude because it's the exact same distance away. It makes the exact same angle with the positive x-axis, right, just on the other end of it. And what that means is that it's symmetric in a sense, right? There is a symmetry between these 2 points. Over the x-axis, I could flip this. And so if there's a mirrored symmetry, the component that gets mirrored, the y component, is going to end up negative on the other end. The y component of the electric field from the positive gets flipped when we look at the negative piece, whereas the x component, because that wasn't flipped, is going to stay the same. The y component of each of these pieces are going to cancel each other out. And because there's an equivalent piece, if I had taken all of my pieces and I line them all up until they meet at the middle, or if I start at the middle and I go all the way out to the outside, there's always an equivalent negative piece that cancels out my y component. But x does not have that same circumstance, right? I'm not mirroring over x, and because of that, there's no negative component to cancel out x. That's the process that I used to take when I was tutoring people. That's, I think, the easiest way to describe it step by step is to go through the substitutions one by one. And just ask yourself every single time, can I integrate this? Why can't I? So all of my substitutions are in gray. If that's clear enough, I don't know how clear that actually ends up being for going through like this. They're a little bit lighter than the others. But it's always the substitution I'm putting in, the arrow up into the part where it's going. These are the types of problems that teach you how to be clever, which is really going to be one of the most useful things. Right? If you can analyze problems and pick them apart piece by piece, and then figure out even more tricks that you might be able to do to get through this faster or with more ease, that's going to be a skill that translates no matter where you end up going. So I don't quite share the same philosophy. I don't know if anybody watched the Dr. Alexander lecture before this one, but he opens this with a scene from Lord of the Rings where they're doing the, "Are you scared? You should be." And I don't feel like that's a necessary thing. It feels a little bit gratuitous to me, but it is kind of funny. But really, it's scary right now, but we'll get better at it. I've got one or two more points that I can talk about on this one. So one of the neat things about this, and one of the kind of the unspoken rules, as we're going to find later on, is what happens if you start going farther and farther away? Before I really talk about that solution, let me go back to this slide. You see this nasty blob that we said, how would we ever find the electric field from this thing? What if I did this? What if I zoomed way out? What if I tried to find the electric field somewhere out here on the right side? What does that blob look like now to you? Kind of looks like a dot. Maybe a dot rough on the edges, but like a dot, right? It's this rule that if you get far enough away from any charge, it eventually looks like a point charge. And that's a nice way to test a lot of your answers. Now, there are exceptions to that. But generally, if I have a charged object that is not infinite or something like that, if there is a finite size to this object, if I can get far enough away from it so that it looks like a dot, I should recreate my electric field from a point charge equation. So we ask, can we do that? We go to our field, we say, what if we make x really, really, really large? Then in that square root, x squared is huge, and L squared over 4 is really, really tiny. And what we get is, that's a negligible difference. Let's get rid of it. Square root of x squared is just x. X times x is x squared. We get kq over x squared. What do you know? It's our point charge again, right? Just like that. So, are we ready to try it ourselves? here's what I'm going to do. I'm going to make some specific things that I'm going to say about this thing. What I want to do is I want to say, let's assume that this rod is the length L over 2. Let's assume that the total charge on this rod is Q over 2. The reason I'm doing this is so that it's like we're taking the rod that we just saw and we're just lopping off the bottom half, right? We're only focused on the top half now, so we've taken off half the charge, we've taken off half the length. That way we can actually a little bit more easily compare and contrast these two problems. But here's how I want you to solve this thing. I am sure that many of you just took fantastic notes on everything that I just did in that derivation. I do not want you to look at those. Do not look at them. Solve this problem from scratch. If you just took it on a sheet of paper, turn that sheet of paper over. Don't let yourself look at those. If you just did it on a draw pad or something else, get a new board, right? Don't look at all of those derivations that I just made. I want you to be able to do this from scratch. At big milestones along this thing, you can check and see if it looks similar. But I'm going to very much recommend that you don't look at what we just did and you try to do this from scratch. You try to go through all the same reason, the same methodology that I just had for that problem and do the problem the exact same way, right? But without looking at it. Remember what you can. If some of the details are a little bit scattered, that's okay, right? This is a prime example to get you started on solving these things yourselves, but you're going to handicap yourself if you try to follow the solution right off the bat. Don't just try to copy down the solution. We're going to have all sorts of varieties of these problems. You need to be able to know how to do these things, and this is your first time that you can try it. Don't waste that time. So let's take a look at this one, right? And right off the bat, before we actually dive into the rest of this, we actually kind of already know what the X component is going to look like. If you went against what I said and looked at the last set of solutions, what we should find right off the bat is that at least our X component should be something like KQ over 2x, x squared plus L squared over 4. And the reason for that is because, okay, well, ignoring whatever is going on in the y direction, the top half of the rod is contributing half of the x field. The bottom half of the rod is contributing the other half of the x field. If we lop off the bottom half, well, half the field is left. So we kind of know what we're looking for already, right? And there's a lot of steps along the way that are going to look very similar. But anyways, let's go ahead and solve this thing out. Let's draw this thing to start. And I'm going to go through the exact same process that I just did last time, maybe a little bit quicker this time around, though. Axes, all that good stuff. Oh, that was supposed to be a box. Mistyped on that one. So we've got a box that looks like that, right? A big rod that's got a total length of L over 2, a total charge of QL, or not QL, Q over 2. And the big reason that I did this is because now we can define lambda as still Q over L. We can just easily compare it to the first time, right? And we can kind of see how a lot of these values might change. So once we do something like that, okay, next steps here. I want to talk about this thing just like I did last time. So I'm going to go through some of these same steps. You might not always need to do these, but for now I will. So let's say I'm looking at a particular piece like that, dq. I know that that piece is defined as lambda times dy, because again, I'm going in the y direction here. Furthermore, I'm interested in what the electric field is at this point down here. So I need to have some R down to that point. Looks like this, roughly, right? Here's R, here's X, here's Y, theta, R hat. So I'm going to take a lot of the same approaches as last time. I'm going to immediately define R hat as I see it's going to be negative every single time. And when I plug in this theta, I want to get a positive X and a negative Y. So cosine theta, positive X, negative Y. Now, piece by piece. I want to find the electric field. To find the electric field, I need to sum up every single piece of the electric field. I don't know how to integrate every single piece of the electric field. I don't know what the bounds of that integration are. So I'm going to replace that by saying the dE is equal to k dq over r squared r hat. Okay, so let's plug that in. This is a step closer, but I still don't know how to integrate dq. So I'll replace that. Let me try to make that a little bit nicer at least. That's so-so. Now, I'm going to actually sub in r hat first before I sub in r, and you'll see why. This is a clever trick I use sometimes. But what I'm going to say is, okay, well, r hat, we see cosine theta I hat minus sine theta j hat. We know that if this is just a big triangle, and this angle right here is theta, then what I can say is that cosine of theta is actually x over r. Sine of theta is actually y over r. Plug both of those in. So let's do this in gray, r hat. And I love to do this one because now what I get when I plug that in, and I might as well pull out the constants, is dy, I shouldn't do that. Let me do x first. So x I hat minus y j hat over r cubed, right? And we can just kind of jump right to that immediately, rather than writing a bunch of extra things. This is all times dy. And again, I'm not replacing dy anymore because I do actually know how to integrate dy. I'm going to go from 0 to plus L over 2. So I do know the bounds of integration for dy. So all I'm doing now is I'm just trying to figure out what is changing as I change y, and how can I represent that change in terms of y so it's properly accounted for when I do the integration. So now we take the same step as before and we say, okay, well, r is square root of x squared plus y squared. Plug it in. And I'm going to split this integral in two, right? I want to treat the x and the y separately. It's just going to be a lot easier that way. So this turns into x dy over we've got all that, right? So far, so good. Now I have to look at my integral table again, and I'm looking for two different things this time around. So the first one I've already got, right? I looked at my integral table last time, and I found something like this. But I also have a second one that I'm going to need, and it's actually conveniently the one right beneath it. But the other value that I'm going to need for my integral table is... Oh, come on. My pen always picks really weird times to just stop working spontaneously. And I still cannot figure out an answer. If anybody uses draw pads consistently and has this exact same issue that I do, can somebody tell me what the solution is? That would be much appreciated, so I don't have to like keep disconnecting and reconnecting during a lecture or something. Well, from the integral table, I'm looking at this thing right here. It looks very, very, very similar. The only difference is that there's now not negative, just x on top which is a lot like what we have. Y dy, x dx, yep, that's the same thing. The answer here is that this is a square root x squared plus y squared under -1. Okay, so we're going to need to plug that in. We're going to need to plug in our old response just as well. And what we're going to find with those then, this is going to be k lambda x, right? That was a constant, so we get to pull that out. X squared times square root x squared y squared. That is under y. Evaluated 0 to L over 2 times I hat. At the very end, kind of a nasty deal, but that's okay. Minus k times lambda times this thing. So this is going to be square root, make sure that's right, yeah. X squared plus y squared under -1, being evaluated from 0 to L over 2 times j hat, of course. Okay, we are almost there. So let's go ahead and plug this stuff in, and what we should find for this one, the 0 term is 0, right? Y is equal to 0 means that this whole term goes to 0, so we're only left with k lambda, let me write that a little bit better. I'm going to have k lambda L over 2 divided by x square root x squared plus y squared. Here is our x component. I'm going to do the exact same thing for y. So the two negatives are going to cancel out. And at first you might be like, hey, wait a minute. There's a plus in front of the j hat, and that is going to be a negative value from our picture? That doesn't make sense, right? That should be pointing down. Just you wait. It'll come out. So we're going to have k lambda. When I first plug in L over 2, so I'm going to leave the k lambda outside for now. When I first plug in L over 2, this is 1 over square root of x squared. Oh, it shouldn't be a y, should it? It should be L squared over 4. There's a question. Is there a reason all of them are pluses instead of plus minus? Because the integral table is essentially a general thing. They're trying to pack as much information in as possible. So this is accounting for the fact that it could be plus or minus. And actually, in this case, if you plug in plus or minus, you're always going to get a negative out. But in the other one up here, if it's x squared minus a squared, for example, the minuses will be in play instead. Whichever one applies. Plus L squared over 4. So we've got that piece right here, and now we're going to subtract away the 0 component. And for here, it's not 0. It's actually square root of x squared, so it's just 1 over x. And now you might see that 1 over x is more negative than 1 over square root of x squared plus L squared over 4 is positive. So this does end up being a negative value when you actually go through and calculate that out. But there's our final answer. Except I just got ahead of myself. I did something not complete. Got one last thing that I need to do. Again, lambda is not one of our given values. We need to plug back in. Q over L is what we said for lambda. So when we plug in the Q over L, this turns into 2x square root x squared plus L squared over 4. I hat I'm not even going to bother with this piece, right? This thing is fine on its own. This can keep doing whatever it's doing already. And there we are. So I have to ask, are we having fun yet? Because I certainly am. Hopefully you are too. If you have any friends in 191 right now, go ahead and show them your homework. There's a lot of steps to these problems, but they are doable, right? They're not impossible things. There's going to be some things that are going to be a little bit weird at first, but we'll talk through all these things, and you're going to get some good practice on these anyways. But they are problems that we are going to continue to do, right? We will need these. I do admit that finding them like this in variables is still a very, very useful thing. It's really cool when you write them out like this, because I keep talking about how, like, we find it at a point charge or something else, but then we'd have to recalculate for different values. But if we find our electric field based on something like this, if you've got something like this, you can plug in for any x, right? If they tell you it's 4 meters away, if they tell you it's 4 centimeters away, if they tell you it's 4 kilometers away, you can plug in for any x. If they tell you the rod is this long or this long, you can plug in for any L. And that's kind of a really neat feature of these things. However, when you are doing these problems, do not just copy solutions, please. You will need to do some of these things, and you need the practice to be able to do these, right? It is not just one of those things that you can look at enough examples and instantly be like, yeah, I know exactly how to do these. You can read through an example and understand every single step, but that is not the same thing as being able to pick apart the problem and figure out what pieces you need to replace yourself. I promise. And that is going to be a useful skill, whether or not you ever need physics again. It's why STEM majors have a lot of flexibility in their careers, and especially physics majors. It's kind of a fun statistic that I want to say 60 or 70% of physics majors don't end up working in physics. They go into other fields because of stuff like this. There's a wide variety of skills, but you guys are all STEM. I mean, that kind of applies to all of us, right? No, those are the people, we're talking the 60 or 70% that got through their bachelor's, that went all the way through, saw all 4 pillars, saw the grand canonical ensemble, and finished the course. And I mean, U sub is useful, but like, it's not as fast. Let's be real. If you know how to do U substitutions very quickly and everything else, go for it, right? Run with that stuff. It's fantastic. Some of these integrals are a lot harder than other ones, though. These 2 integrals look very, very similar, but they're a lot harder to do. Like one of them significantly harder than the other. Okay. So, we've got not a lot left, but let's look at our first special case. And here is where we run into an issue. When I said that if you're far enough away it looks like a point charge, here's kind of a weird exception. Let's imagine that this rod is infinitely long. So instead of the bounds being plus L over 2 and minus L over 2, let's take those all the way out to infinity. What happens to the integral then? It's still solvable, by the way. It's still a totally solvable thing. We can plug those values in. It's just what we find when we do that, you need to take some limits, but when you plug everything in, we get this result down here, 2k lambda over x. That's kind of a neat feature, because for one, it's telling us that, okay, well, not over r squared is kind of cool to begin with. Oh, there we go. I'll be a little bit more to the side, or this side, I guess. It's always flipped. There we go. That's the end of the equation. But what we find here is that, for one, it doesn't change with 1 over r squared, which is a little bit strange, right? I made the point earlier that I said that we should always be able to recreate the point, you know, the field from a point charge equation. This is kind of an exception, though, because I want you to think about what happens if this field is actually, or if this is actually an infinitely long line. When are you sufficiently far away from this thing that it looks like a dot? You never are. It doesn't matter how far away you get, it still looks like an infinite line. So the point charge kind of rule doesn't apply here. And another justification for how this thing goes is you have to imagine, what if I'm looking at my point right here, right? Some of these close by pieces are a lot stronger, right? And they're all kind of adding up like this. But if I look at some of the farther away pieces, I start to see a lot of things like this that are going way out to the side that have a little bit of an X component, but for the most part, it's mostly in the Y, and all the Y's are canceling out still. By the time we get out here, those same points that were mostly in the Y direction are now a little bit more in the X direction, but all of the pieces are a little bit weaker than they were before. And what that means is that as we still get farther away from the rod, it does decrease in the strength of the electric field, but it decreases at a slower rate as compared to just a finite rod or a point charge as we might expect to normally see them. So kind of a fun thing, right? But this is a special result. We will end up using this quite often because even if these fields, or even if these lines are not infinite per se, if you have a very long wire and you want to know what the electric field is, 1 centimeter away from that wire, the infinite line equation is still a useful approximation because, like, let's be honest, is the ends of that thing really going to make a difference? No, it's not, right? We just mentioned that it's not going to make a difference. So as long as you're close enough to a wire or to a rod that's got charge, you can safely use the infinite field line and it's going to work out just fine, right? That'll give you the right answer. But keep in mind that it's not just going in the X direction. This is radially away. If I took this thing and spun it around so that I was looking at a bunch of different X's, I go all the way around, right? It looks equivalent from no matter which direction I look at this thing. It actually kind of looks like one of these bristle brushes, what the electric field would look like, right? Going radially outward from the wire. And then depending on whether that charge is positive or negative, that will tell you about the sign of the field. Naturally, positive radiates the charge, or radiates the field out, negative pulls the field in. We talk about this in terms of lambda because in the case of an infinite line of charge, how long is infinite? Infinity. How much charge is on an infinitely long wire? Infinity. But how strong those infinities are might change. So we instead talk about lambda because it's a charge density, and that's something that no matter what the length of this wire actually is, that is something that we can quantify, right? We can have more or less density, even if it's infinitely long. But it's kind of this neat feature that it goes over 1 over r. So, let's try this. Let's imagine we have 2 infinitely long wires. One is charged with a positive lambda. The other is charged with a negative lambda, right? They're going into and out of the page, so they're like poking you in your eye if you're looking at this the wrong way. I want you to find the electric field strength at that black dot as shown in the picture. There is a symmetry argument that you can make here that you can avoid some of the work from. And if you're not sure what it is, don't worry about it. The math will work itself out even if you go through all the steps rigorously anyways. But when I solve the problem, I'll talk about that symmetry step. I made some mention at the very beginning that maybe, just maybe, we can avoid doing more work and we can instantly jump to an easier solution. And I'm going to say we can cut our work by about a quarter, actually, if we're clever with it. So here's what I'm going to say. Let's look at first the distance between each of these. We can agree, hopefully, that I've got essentially 2 identical triangles on either side, right? Hypotenuse R here is the same as hypotenuse R here. They're the same. So if they're of equal magnitude and charge density, then what I'll call E plus, the full vector, the magnitude of E plus is equal to the magnitude of E minus, right? They should be the same. Okay, furthermore than that, let's keep going with this idea. Let's draw out the 2 r hats. So I've got what I'll call r hat plus, and I'm going to draw this bad, but that's okay, and r hat minus. Okay, well, each of these, again, is kind of like mirrored of the other, right? That angle is the same as that angle right there. Okay, so that's cool, but I'm running into a little bit of an issue because where I would love the two x components to cancel out, unfortunately, this field points this way. It's a negative charge, so the field points like that. Okay, and let's draw in the red one as well while we're here. The positive field points like that. And I know sky blue is not the same as teal, but I've got a limited palette. Okay, well, we almost saved ourselves a bunch of work, but wait a minute. Before we kind of give up on that idea completely, isn't it true that these angles, so let's do 3 bands for that one, are also the same? If we flip these two, if these two angles were the same, then these two angles should also be the same. And they're the same magnitude. That would suggest to me that if I was looking at the x component, let me do that the other way around. If I was looking at the x component of E plus, it would be equal to the x component of E minus. But on the other hand, for the y component, it's going to be negative. What that basically means is that my y components are going to cancel out. My x components are going to be the only one that matters. But even more than that, that saves me half of my work, but I can save another half by looking at the fact that they are the same magnitude, and if they're the same magnitude and the x components are equal between the two, I really only need to find the magnitude of one and double it and call it a day. So let's do just that. We go to this problem right here, right? We know what the picture should look like. We've got this line right there. That should have been in black, but you know what? We're going to leave it because we're on a speed run for this thing right now. We're a distance r away from this thing. R, in this case, is going to be, well, I am looking, so if I've got this triangle, I'm going to have essentially square root of y squared plus d squared over 4. With me so far? My r hat goes out like this. What is this angle theta right here? Well, it's the same as this angle theta down here, and I can define that. Well, better yet, let's do this. I only care about the x component, right? Phi of r hat is equal to cosine of theta I hat plus sine of theta j hat. And I really don't care what happens to the j hat piece. I only care about the cosine. Then I could just say, okay, well, take that whole thing, and I'm going to focus on the fact that cosine of theta is equal to adjacent over hypotenuse. So we go to our x component. Or let's go ahead and start with the magnitude first. Let's do that first. Magnitude is going to be k, 2 times k times lambda over r. Fantastic. I don't have a lot else to do with this, really, right? 2k lambda. Let's just go ahead and replace r. All those pieces right there. Now we want the x component of this thing, so we are going to multiply by only the x component, right? The cosine of theta. So this is going to become 2k lambda over, well, r is showing up a second time, so that'll be r squared on the bottom, right? I probably should have left that, actually. Y squared plus d squared over 4 times d over 2 can cancel out the 2. This turns into k lambda times d over y squared plus d squared over 4. And just like that, without needing to solve out all of the other pieces and then sum them up together, that is my net. Oh, just kidding. Oh, one more step. I jumped the gun. E net is equal to 2, let's do vector style, times the x component. I need to not jump the gun like that. What I should end up with then is 2k lambda d over y squared plus d squared over 4. And there we are. Put in an I hat so that it's accurate. With that, that actually closes out 23-2. Next time we'll get the chance to take a look at some other very special fields and some other types of integrals that I might do. More things with 1D charges, all sorts of goodies like that. But until then,